two genes, one for color and one for shape. Genes for color would be the dominant gene would be purple, and the recessive gene green, and that for shape, dominant gene would be circular and recessive gene would be, well, a triangular shape, right? So suppose we are to cross two individuals which are heterozygotes for both genes. So that would mean there would be capital A, little a, capital B, little b, by capital A, capital B, little b. So we first have to find out the possible genotypes, of, sorry, the possible gametes of our different parents. So going across this A, this capital A of this capital B, and this capital A of this little b. So we would get capital A, capital B, and capital A, little b, and this small a of this big B, this small a again with this little b. So we'll get little b, capital B, little a, sorry, capital B, and little a, little b. So this would be our possible gametes for both parents, seeing that both of them are heterozygotes for color and shape. So we now have to draw a 4 by 4 Punnett square. So we can just erase this extra. So one parent is going to go on the top and one parent is going to go on the left. So we're going to have our possible gametes: capital A, capital B, capital A, small b, little a, capital B, little a, little b, capital A, capital B, capital A, little b, little a, capital B, and little a, little b. That's supposed to be a B right here. So now we're going to cross all different gametes. So we're going down and across. So capital A, capital B, capital B, capital B, capital A, capital A. Oh, I made a mistake. Let's just go back a bit. So this is going to be capital A, and big B, big B, big A, big A, big B, little b, big A, little a, and big B, big B, and big A, little a, big B, little b. So on to our second row, down and across, capital A, capital A, capital A, little b. So I'm just going to finish this off right here. So just give me a moment. You can follow on. Or just skip ahead. Right, so these are our possible crosses between our gametes. So the possible phenotypes, that is our phenotypic ratio, is going to be purple and round, uh, purple and triangular. It's gonna be green and round, or green and triangular. So we're going to have for our purple and round individuals, for our purple and round individuals. So in order for individual to be purple and round, they have to have the dominant gene for purple and dominant gene for the shape round. So they have to have at least one capital A and one capital B. So we have 1, 2, 3, 4, 5, 6, 7, 8. We have 9 said individuals. So for our purple and triangular, they have to be dominant. They have to have at least one dominant allele for purple, and they have to be a double recessive. So one, at least one capital A and two lowercase b's. So that's going to be 1, 2, 3. 3 individuals. For green and round, it's going to be double small a as a double recessive and at least one capital B. So 1, where are the others? 2 and 3, and we're only going to have one where you have a double recessive for both shape and color. So we're going to get the ratio 9 to 3 to 3 to 1. So out of every 16 individuals, 9 of them will be purple and round. Out of every 16, 3 will be purple and triangular. Out of every 16, 3 will be green and round. And out of every 16, 1 will be green and triangular. So suppose we had 144 individuals, right? How many do we expect to be purple and round, purple and triangular, green and round, and green and triangular? So the individuals to whom we expect to be purple and round is going to be 9/16 of 144. So it's going to be 9 over 16 times 144 for the individuals which are purple and triangular. Is going to be 3 over 16 times 144. The individual who is green and round is going to be the same, 3 over 16 times 144. And for the individual which is green and triangular is going to be 1 over 16 times 144. So this, they are going to equate to, this should be 86, 27, 27, and 9. Please forgive me if I am wrong, but you can just do the calculations yourself. So this would be, these would be our expected values. This would be our expected values. However, after we actually counted the number of individuals who were purple and round, purple and triangular, green and round, and green and triangular out of the 144 offspring, we found that 81 of them were purple and round, 26 of them were purple and triangular, 24 of them were green and round, and 8 of them were green and triangular. So this difference between our observed and our expected values, is it due to some chance, or is it because we made a mistake? We made a mistake in the crossing of the individuals or in our calculation. So we can hypothesize using a null hypothesis. We can hypothesize that the difference between our observed and our expected values is not significant. So this difference, it can be due to random chance. That would be our null hypothesis. So there's a we'd call special thing in math we'd call our chi-squared test, or chi-squared test, however you want to pronounce it. And this test states that if we have our observed minus our expected all squared over our expected, and it would be the sum of all those values. So we have our observed, we have our expected. So let's calculate our observed minus our expected. So 81 minus 86, I just have a slight feeling that there's an error somewhere. Let me grab my calculator. Alright, I'm sorry about that. So these values are to change. So 9 over 16 times 144, that is equal to a1, and observed our observed would be a 6. While I'm at it, let me just cross check this right here. Both be 27. So yeah, so our observed minus our expected, which would be 86 minus 81, that would be, let me just go back to my gray color. So 81 minus 86 is 5. 27 minus 26, sorry, 26 minus 27 is negative 1. 24 minus 27 is negative 3. And 8 minus 9 is negative 1. So now we have to square these values right here. Square these values, because it's going to be our observed minus our expected, all squared, like so, all squared. So 5 squared is 25. Negative 1 squared is positive 1. Negative 3 squared is 9. And negative 1 squared again would be positive 1. So the next step in our formula will be to divide by our expected. So we're going to be our observed minus our expected, all squared divided by our expected value. So it's going to be 25 divided by 81, which is going to be 0.31. Then it's going to be 1 divided by 27, which is 0.04. 9 divided by 27, 0.33, and 1 divided by 9, which is going to be 0.11. Now we have to add up all these values because it's the sum of this right here. It's the sum. So we say 0.31 plus 0.04 plus 0.33 plus 0.11, and that would be 0.79. So our value for our chi-squared test, is equal to 0.79. But what is the significance of this value? What is the significance for this value? Before we get into that, we have to first find our degree of freedom. So the way in which we'd find our degree of freedom, seeing that we have 4 values, 4 data points for our ratio, is going to be 4 minus 1. So our degree of freedom is going to be 3. We'll see the significance of this shortly. So this is our table showing our critical values for our chi-squared test. And seeing that our degrees of freedom is 3, we only going to focus on these values here. Now in genetics, we have a critical value of 0.05. Any value that is to the right of this, that is, it's lower than this, it means that the difference between our observed and our expected values is significant. And any value that is greater than 0.05, it would mean that it is insignificant. So if the difference is insignificant, that would mean we accept our null hypothesis. If the difference is significant, that would mean we reject our null hypothesis. So where does 0.79 fall along this row here? 0.79 probably it's not even in the table. It probably falls somewhere all the way over here. So we can say the difference between our observed and our expected is insignificant.